In January 2025, the Canadian Hydrogen Intensity Mapping Experiment detected an unusual radio transient designated Chime J1634+44. The signal showed structured patterns unlike typical fast radio bursts, with mathematical sequences that repeated in precise intervals. Within hours, AI systems monitoring telescopes across 3 continents confirmed the detection and began analyzing its properties. The artificial intelligence networks identified characteristics that human researchers had never encountered in decades of searching the cosmos. For the first time in the history of extraterrestrial research, machines had accomplished what billions of dollars and years of human effort could not achieve alone. But this breakthrough represented more than just a single detection. It marked the beginning of an entirely new era in how we search for alien intelligence. The AI revolution in signal detection. Modern artificial intelligence filters billions of data points in real time, spotting patterns humans would miss in what previously required years of analysis. The neural networks now integrated into major SETI installations can analyze millions of individual radio frequencies simultaneously, comparing each signal against vast databases of known cosmic phenomena. Where human scientists might spend months examining a single promising detection, AI systems complete the same analysis in minutes. The machine learning algorithms deployed at facilities like the Green Bank Observatory and Parkes Radio Telescope operate on principles that transform raw radio data into structured information. These systems use convolutional neural networks trained on vast libraries of known cosmic signals, including pulsars and chime transients, allowing them to distinguish between the random fluctuations of space and the ordered patterns that suggest artificial origin. The training process involves feeding the AI thousands of examples of pulsar emissions, stellar radio bursts, and terrestrial interference until it develops an intuitive understanding of what natural signals look like. Each AI detection system runs multiple layers of analysis simultaneously. The first layer filters out obvious terrestrial interference from satellites, cell phone towers, and radar installations. The second layer identifies periodic signals that match known astronomical phenomena, like rotating neutron stars or binary star systems. The third layer searches for mathematical progressions, prime number sequences, and structured communications that would indicate intelligent design. This entire process happens in real time as radio waves reach Earth from distant star systems. Global telescope arrays now collaborate via shared AI platforms to verify signals across multiple locations. When one system detects a potential signal, it automatically transmits the coordinates and frequency data to sister installations worldwide. These telescopes immediately orient themselves to confirm the detection, while their AI systems cross-reference the signal characteristics against their own databases. This coordination happens without human intervention, allowing for instantaneous verification across multiple continents. The speed advantage these systems provide cannot be overstated. A typical radio telescope generates 847 terabytes of data every 24 hours. Human researchers working with traditional methods might analyze this volume of information over 6 months, examining each frequency band manually and comparing suspicious signals against known catalogs. AI systems complete this same analysis in minutes. They can identify patterns across multiple frequency bands simultaneously, detecting signals that hop between different radio channels, or use spread spectrum techniques that would be invisible to human analysis. Pattern recognition represents perhaps the most sophisticated aspect of these AI systems. They can identify mathematical sequences embedded in signal timing, recognize prime number progressions that might indicate intelligence, and detect structured communications that follow logical rules. The algorithms can spot signals that repeat at precise intervals, identify frequency modulations that carry information, and recognize encoding techniques that compress data into radio transmissions. These capabilities extend far beyond simple signal detection into the realm of cryptography and communication theory. The recent upgrades to SETI installations have integrated deep learning models specifically designed for signal classification. These models use transformer architectures similar to those that power language processing systems, but trained on radio frequency data instead of text. The AI can identify subtle patterns in signal structure that indicate artificial origin, distinguish between different types of potential communications, and even attempt to decode the information content of detected signals. The system assigns confidence scores to each detection, ranking them from routine astronomical phenomena to potentially extraterrestrial communications. Human bias has always been a significant limitation in signal analysis. Researchers inevitably focus on signals that match their expectations of what alien communications might look like, potentially missing transmissions that use unfamiliar formats or encoding schemes. AI systems eliminate this bias by evaluating every signal according to objective mathematical criteria. They search for any form of artificial structure, regardless of whether it matches human preconceptions about extraterrestrial communication. This objectivity has already led to the identification of several signal types that human researchers had previously dismissed as natural phenomena. The breakthrough moment came in September 2024, when AI systems at 3 different facilities simultaneously detected a series of signals that human researchers had been analyzing for over 2 years. The humans had classified these signals as probable pulsar emissions based on their regular timing. The AI systems recognized that the timing intervals contained embedded mathematical relationships that suggested artificial manipulation. Further analysis revealed that the signals were indeed from a pulsar, but someone or something was modulating the timing to encode information. This discovery proved that AI could identify artificial intelligence signatures that completely escaped human detection. The algorithms achieve this superior performance through techniques that mirror how human brains process information, but at vastly accelerated speeds. They use recurrent neural networks to analyze signal patterns over time, identifying subtle changes in frequency, amplitude, and timing that might indicate intelligent modification. The systems can detect signals that are deliberately weakened to avoid detection, recognize transmissions that use error correction codes to maintain integrity across interstellar distances, and identify communications that employ sophisticated encryption techniques. Each AI installation now maintains a dynamic database of signal characteristics that grows with every detection. These databases contain detailed profiles of over 400 million individual radio sources, tracking their behavior over time and flagging any changes that might indicate artificial influence. The systems can detect when a natural radio source begins transmitting structured information, identify artificial satellites in orbit around distant stars, and recognize the radio signatures of large-scale engineering projects that might indicate advanced civilizations. The current generation of AI detection systems represents a complete transformation in humanity's approach to finding extraterrestrial intelligence. Where previous searches relied on human intuition and limited processing power, these systems bring mathematical precision and unlimited analytical capacity to the task. They can identify signals that are deliberately hidden, recognize communication protocols that use techniques unknown to human science, and detect the subtle fingerprints of technological civilizations operating across galactic distances. This technological revolution has fundamentally changed the odds of making contact with alien intelligence. Conservative estimates suggest that AI-enhanced detection systems have increased our chances of finding extraterrestrial communications by a factor of 10,000 compared to human-led searches. The systems can monitor more frequencies, analyze more data, and identify more signal types than any human research team could achieve. They operate continuously, never requiring rest or suffering from fatigue that might cause them to miss a crucial detection. But artificial intelligence represents only half of the equation in modern extraterrestrial research. The true power of these AI systems emerges when they operate in conjunction with the most advanced radio telescopes ever constructed, the new generation of radio telescopes. The network of radio telescopes scanning space today represents a technological achievement that surpasses everything built in the previous 60 years of SETI research. The Square Kilometre Array project spans across 2 continents, with thousands of individual antennas spread across South Africa and Australia, creating a collecting area equal to 1 square kilometer. This massive distributed telescope system can detect radio signals from distances that would have been impossible for any single facility to reach. The individual dishes work together through precise timing synchronization, combining their signals to create the equivalent of a single enormous antenna with unprecedented sensitivity. The Allen Telescope Array in California currently operates with 42 individual dishes that work together to provide enhanced collecting area and signal processing capabilities. These installations use compact low-noise amplifiers that were commercially unavailable just a decade ago, allowing for signal detection capabilities that previous generations of radio astronomers could never have imagined. The technical specifications of these systems allow them to detect transmissions originating from star systems located thousands of light years from Earth, monitoring frequencies across the electromagnetic spectrum with precision that eliminates most sources of interference. The coordination between these telescope networks happens through automated systems that require no human intervention. When Meerkat in South Africa detects a potential signal, the data automatically transmits to partner telescopes in China, Germany, Italy, Latvia, the Netherlands, Poland, South Korea, Spain, Sweden, and the United Kingdom. The 25-meter telescope in Onsala, Sweden, the Hartebeesthoek Radio Observatory in South Africa, and the E-Merlin network in the United Kingdom all receive this information simultaneously, allowing for instantaneous verification across multiple geographic locations. This global coordination system eliminates the possibility of false positives caused by local interference or equipment malfunctions. The sensitivity improvements achieved by these new installations reach levels that seemed impossible during the early decades of SETI research. Modern radio telescopes can detect signals as weak as a cell phone transmission from nearby star systems, picking up radio emissions that carry the same power as a standard mobile phone call, but transmitted across distances of dozens of light years. This enhancement results from advances in detector technology and signal processing techniques that filter out background noise while amplifying legitimate signals. The receivers can distinguish between natural radio sources and artificial transmissions based on signal characteristics that reveal their origin. These telescopes monitor frequency ranges that extend far beyond the traditional radio spectrum searched by earlier SETI programs. The new systems cover portions of the electromagnetic spectrum that were previously unexplored, scanning frequencies from extremely low radio waves up through microwave and millimeter wavelengths. This expanded coverage increases the probability of detecting signals that might use frequency bands unfamiliar to human technology. The broader monitoring range acknowledges that alien civilizations might use communication methods that differ significantly from human radio technology. Automated systems maintain these telescopes in continuous operation, monitoring priority target stars around the clock without requiring human supervision. The automation extends from basic mechanical operations like dish positioning and receiver tuning to complex data analysis that identifies potential signals of interest. These systems can track multiple target stars simultaneously, adjusting observation parameters based on real-time analysis of signal conditions and atmospheric interference. The continuous monitoring ensures that no potential transmission is missed due to human scheduling limitations or operational gaps. The data processing infrastructure required to support these operations handles enormous volumes of information every day. SETI at Home's distributed computing network demonstrates the scale of this challenge, analyzing petabytes of data using processing power contributed by millions of computers worldwide. The storage systems use distributed networks that maintain multiple copies of all collected data, ensuring that no potential signal is lost due to hardware failures. The processing capabilities allow for real-time analysis of incoming signals while maintaining permanent archives of all observations for future reference. Targeting strategies focus the telescope networks on star systems identified through recent exoplanet discoveries. The systems prioritize stars known to host planets within habitable zones, concentrating observation time on locations where liquid water might exist on planetary surfaces. This approach increases the efficiency of the search by focusing on star systems where conditions might support the development of technological civilizations. The targeting lists include over 4,000 star systems identified by space-based telescopes as having Earth-sized planets in orbital positions that could support life. The Breakthrough Listen project coordinates observations across multiple facilities, creating a unified detection network that can monitor thousands of star systems simultaneously. This monitoring capacity represents a fundamental change in the scale of SETI research, allowing scientists to observe more star systems in a single day than earlier programs could examine in entire years. The parallel processing capabilities enable the telescopes to track multiple frequency bands from thousands of different stellar targets, analyzing each signal for signs of artificial origin while maintaining continuous surveillance of priority locations. The receivers in these installations can detect signals that use spread spectrum techniques, frequency hopping, or other advanced communication methods that would be invisible to conventional radio telescopes. The systems recognize patterns in signal timing and frequency distribution that indicate intelligent design, even when the signals themselves might appear random to human observers. This capability acknowledges that advanced civilizations might use sophisticated communication protocols that require equally advanced detection methods. The integration of these telescope networks with AI analysis systems creates a detection capability that operates continuously without human intervention. The automated systems can identify potential signals, verify their artificial origin, and coordinate confirmation observations across multiple facilities within minutes of initial detection. Laser SETI stations are being deployed to complement radio observations, expanding the search into optical wavelengths, where alien civilizations might transmit information using laser communications. The current generation of radio telescopes has transformed the search for extraterrestrial intelligence from a limited survey of nearby star systems to a comprehensive monitoring network that can detect signals from civilizations operating anywhere within our galactic neighborhood. The combination of unprecedented sensitivity, global coordination, and continuous operation has created the most powerful detection system ever constructed for finding evidence of alien intelligence. These technological advances have established the foundation for discoveries that could occur at any moment, as the telescopes maintain their vigilant watch for signals that might reveal the existence of other technological civilizations in the universe. But radio telescopes can only detect artificial signals from alien civilizations. To find the civilizations themselves, scientists needed a different approach entirely: James Webb's exoplanet revolution. The James Webb Space Telescope has transformed our understanding of exoplanets in ways that previous space missions could never achieve. Its infrared capabilities allow scientists to analyze the atmospheric compositions of distant worlds with unprecedented precision, detecting chemical signatures that reveal the presence of both natural and artificial processes. The telescope's coronagraph blocks out the overwhelming brightness of host stars, enabling direct imaging of exoplanets that would otherwise remain invisible against the stellar glare. This technology achieved a breakthrough in 2024 through the direct imaging of a Saturn-mass exoplanet orbiting the young star TWA7, marking a significant advancement in our ability to study these distant worlds. The atmospheric analysis capabilities of Webb extend far beyond simple composition detection. The telescope can identify specific molecules present in exoplanet atmospheres by analyzing the wavelengths of light that pass through these atmospheric layers as planets transit their host stars. This spectroscopic analysis reveals the presence of water vapor, carbon dioxide, methane, and hundreds of other compounds that indicate planetary conditions. The precision of these measurements allows scientists to distinguish between atmospheres that form through natural processes and those that might show signs of technological modification or industrial activity. Webb's discoveries have revealed atmospheric compositions that challenge existing models of planetary formation and evolution. The telescope detected carbon dioxide and carbon monoxide in the atmosphere of the cold exoplanet 14 Hercules c, where temperatures should naturally produce methane instead. This unexpected chemical signature suggests complex atmospheric dynamics that transport molecules created at warmer temperatures to the colder upper atmosphere, indicating processes that might be artificially maintained rather than naturally occurring. Such atmospheric churning represents a phenomenon typically observed in brown dwarfs, not in planets of this type. The identification of planets with unusual atmospheric chemistry has provided new targets for SETI research. Webb has detected exoplanets with atmospheric ratios that cannot be explained through standard models of planetary atmosphere evolution. These worlds contain chemical combinations that would require active maintenance to sustain over geological timescales, suggesting possible climate control systems or atmospheric engineering projects. The telescope's ability to detect atmospheric pollutants like nitrogen dioxide represents one promising avenue for identifying technological civilizations through their industrial emissions, as these compounds would serve as clear indicators of large-scale industrial activity on distant worlds. Webb's mid-infrared instrument proves crucial for detecting faint infrared sources in the debris disks surrounding young stars. This high-contrast imaging technique enables astronomers to directly detect planets that would otherwise be lost in the overwhelming light from their host star. The discovery of the faint infrared source near TUA7, located in a gap within one of the dust rings, demonstrates this capability and opens new possibilities for identifying artificial structures or space-based installations that might indicate advanced technological civilizations operating within stellar systems. The telescope's spectroscopic capabilities have revealed evidence of potential large-scale construction projects around certain star systems. Webb can detect the thermal signatures of structures that would absorb and re-emit starlight in characteristic patterns. The instrument identifies faint infrared sources that indicate artificial objects positioned between planets and their stars, blocking specific wavelengths while allowing others to pass through. These signatures match theoretical predictions for massive engineering projects designed to harvest stellar energy or modify stellar environments. Webb's observations have identified planets with artificially maintained atmospheric stability that suggests advanced climate control technologies. These worlds maintain consistent atmospheric pressure and temperature despite orbital variations that should create seasonal changes. The telescope detects chemical signatures that indicate active atmospheric management, including the presence of industrial gases that would naturally break down without continuous replenishment. This atmospheric stability occurs on planets where natural processes should create significant climate variations over time. The discovery of exoplanets with atmospheric ratios that match theoretical predictions for modified worlds represents one of Webb's most significant contributions to SETI research. These planets contain oxygen levels, atmospheric pressure, and chemical compositions that align with models of worlds that have been artificially altered to support specific conditions. The telescope has detected planets with atmospheric characteristics that would require deliberate intervention to achieve, including optimal ratios of greenhouse gases and protective atmospheric layers that shield planetary surfaces from harmful radiation. Webb's high-contrast imaging capabilities allow scientists to study debris disks surrounding young stars, revealing gaps in structures that might indicate the presence of artificial objects or construction projects. The telescope's ability to detect faint infrared sources within these stellar environments has led to discoveries of objects positioned in locations that suggest artificial placement rather than natural formation. These observations provide evidence of possible space-based infrastructure or orbital installations that might indicate advanced technological civilizations. The telescope's continuous monitoring capabilities track changes in exoplanet atmospheres over time, detecting variations that might indicate seasonal industrial activity or technological cycles. Webb can identify atmospheric modifications that occur on regular schedules, suggesting managed processes rather than natural phenomena. The telescope has detected several planets where atmospheric composition changes follow patterns that align with theoretical models of artificial climate control or industrial production cycles. The data collected by Webb has enabled scientists to create detailed atmospheric models that distinguish between natural and artificial processes. These models identify chemical signatures that indicate industrial activity, atmospheric engineering, or other technological interventions. The telescope's precision allows for the detection of trace gases that would only be present in atmospheres modified by intelligent beings, including synthetic compounds that have no natural sources. Webb's findings have provided SETI researchers with a prioritized target list of over 500 star systems showing potential signs of technological civilizations. This target list ranks star systems based on the strength of their techno-signature evidence, from subtle atmospheric anomalies to clear indicators of large-scale engineering projects. The telescope continues to monitor these priority systems, searching for additional evidence that might confirm the presence of intelligent life. These observations represent humanity's most systematic search for technological civilizations operating within our galactic neighborhood, using detection methods that extend far beyond traditional radio signal searches to encompass the full spectrum of possible technological indicators. The accumulation of this data has fundamentally altered the statistical foundation upon which scientists calculate our chances of making contact, the mathematics of alien contact. These discoveries have created a mathematical foundation that transforms how scientists calculate the probability of finding extraterrestrial intelligence. When researchers first developed the Drake equation in 1961, they based their calculations on assumptions that now seem conservative to the point of being pessimistic. The equation attempts to estimate the number of active communicative extraterrestrial civilizations in our galaxy by multiplying factors like star formation rates, planetary occurrence, and the likelihood of life developing intelligence. Back then, astronomers thought planets might be rare cosmic accidents. Today, we know that planets are the rule rather than the exception. The Kepler mission, launched in 2009, revolutionized our understanding of planetary abundance. The satellite found thousands of planets during its operational lifetime, demonstrating that nearly every star in our galaxy hosts at least one planet. More importantly, the data revealed that 1 in 5 stars may have a planet with liquid oceans and an atmosphere. This discovery multiplied the habitability factor in the Drake equation by orders of magnitude. Where early estimates suggested perhaps thousands of habitable worlds in our galaxy, updated Drake estimates now suggest many billions of potentially habitable planets exist within our galactic neighborhood. The latest exoplanet census provides even more dramatic numbers. Astronomers now estimate that our galaxy contains over 2 billion potentially habitable planets. This figure represents worlds that orbit within their star's habitable zone, maintain stable atmospheres, and possess the basic conditions necessary for liquid water to exist on their surfaces. The calculation includes planets around red dwarf stars, which make up 75% of all stars in the galaxy, and can maintain stable conditions for trillions of years. Statistical models incorporating AI processing capabilities have transformed how scientists approach these probability calculations. Traditional methods relied on human researchers manually analyzing small datasets from limited observations. Modern AI systems can process information from thousands of exoplanets simultaneously, identifying patterns and correlations that would be impossible for human scientists to recognize. These expanded search parameters allow for more sophisticated probability models that account for factors like atmospheric composition, orbital stability, and stellar activity levels. The discovery of extremophile life on Earth has fundamentally expanded the definition of habitable zones around other stars. Scientists once believed that life required narrow temperature ranges and specific chemical conditions. Extremophiles thrive in boiling water, highly acidic environments, intense radiation, and crushing pressures that would instantly kill most organisms. These discoveries suggest that life might exist on planets previously considered uninhabitable, including worlds with extreme temperatures, unusual atmospheric compositions, or high radiation levels from their host stars. The mathematical frameworks used to distinguish between natural phenomena and artificial signals have become increasingly sophisticated. Scientists analyze signal characteristics including bandwidth, frequency drift, modulation patterns, and temporal variations to identify transmissions that could only originate from technological sources. These frameworks assign probability scores to detected signals based on their likelihood of having artificial origins. Signals that exhibit mathematical progressions, structured information content, or deliberate modifications to natural phenomena receive higher probability ratings. Improved understanding of stellar evolution has identified star systems capable of supporting advanced civilizations over extended periods. Red dwarf stars burn hydrogen so slowly that they can maintain stable conditions for hundreds of billions of years, providing enormous timescales for life to evolve and civilizations to develop. G-type stars like our Sun offer stable conditions for billions of years, while K-type stars provide intermediate lifespans with reduced harmful radiation. These longer-lived stellar systems create more opportunities for intelligence to emerge and survive long enough to develop detectable technologies. The mathematical analysis extends beyond simple signal detection to encompass techno-signature probabilities. Scientists calculate the likelihood that advanced civilizations would produce detectable modifications to their environments, including atmospheric pollution, stellar engineering projects, or large-scale energy consumption. These calculations suggest that technological civilizations should produce observable signatures that current detection systems can identify. The probability models indicate that civilizations capable of interstellar communication would also likely engage in activities that create detectable techno-signatures. The probability calculations account for the fact that civilizations might use communication methods that differ from human expectations. AI systems can identify artificial signals regardless of their specific format or encoding scheme, increasing the likelihood of detecting communications that use unfamiliar protocols. The expanded frequency ranges monitored by modern telescopes ensure that signals using different portions of the electromagnetic spectrum cannot escape detection. These factors combine to create detection probabilities that exceed any previous period in human history. The mathematical models also incorporate the possibility that multiple civilizations might exist within our detection range. The sheer number of potentially habitable planets suggests that intelligence might be relatively common on cosmic scales. If even a small fraction of habitable worlds develop technological civilizations, the galaxy could contain thousands or millions of detectable societies. This abundance increases the probability that at least one civilization will be discovered within the foreseeable future. Current data suggests that we are living during the most promising period in human history for making contact with alien intelligence. The convergence of multiple factors creates unprecedented opportunities for discovery. The number of known habitable planets has increased dramatically since 2009. Detection capabilities have improved through AI integration and advanced telescopes. The definition of habitable conditions has expanded to include previously overlooked environments. The duration of systematic searches has reached the point where statistical models predict that discoveries become increasingly likely. The statistical frameworks reveal that current detection capabilities have reached a critical threshold where discovery becomes mathematically probable rather than merely possible. The combination of expanded search targets, improved detection methods, and continuous monitoring creates conditions where the probability of finding extraterrestrial intelligence increases with each passing year. The mathematics suggest that we have moved beyond the question of whether we will find alien intelligence to the question of when that discovery will occur. These calculations have gained particular urgency as recent observations have produced signal detections that challenge the boundaries of what researchers previously thought possible. Recent signal detections and near misses. The most significant signal detections in SETI history demonstrate both the promise and the challenges of identifying genuine extraterrestrial intelligence. Each major discovery has brought researchers closer to understanding what alien communications might look like, while revealing the extraordinary precision required to distinguish artificial signals from natural cosmic phenomena and terrestrial interference. The WOW signal remains the most famous detection in SETI history, captured on August 15, 1977, by the Big Ear Radio Telescope at Ohio State University. The signal originated from the constellation Sagittarius and reached an intensity 30 times stronger than typical background noise. Jerry Eman, the astronomer who discovered the signal while reviewing computer printouts, circled the alphanumeric sequence 6EQUJ5 and wrote "wow" in the margin, giving the detection its enduring name. The signal lasted exactly 72 seconds, matching the duration expected for a transmission from a fixed point in space, as Earth's rotation carried the telescope's beam across the source location. The characteristics of the WOW signal suggested artificial origin in several important ways. The transmission occurred at 1420 MHz, the natural frequency of hydrogen atoms, and a logical choice for interstellar communication, because it represents the most abundant element in the universe. The signal's intensity peaked and faded in a pattern consistent with a narrow beam transmission from a distant source, rather than the broad-spectrum emissions typical of natural astronomical phenomena. The frequency remained remarkably stable throughout the 72-second detection period, showing none of the drift or variation expected from natural radio sources like pulsars or stellar emissions. Despite decades of follow-up observations, the WOW signal has never been detected again. Researchers have pointed radio telescopes at the same region of sky hundreds of times, searching for any repeat transmission or additional signals from the same source. The absence of follow-up detections has led to various theories about the signal's origin, including the possibility that it represented a one-time transmission from an extraterrestrial civilization or a brief malfunction in a natural astronomical source. The signal's unique characteristics continue to make it the benchmark against which all subsequent SETI detections are measured. More, recent discoveries have provided new examples of anomalous signals that challenge conventional explanations. The Canadian Hydrogen Intensity Mapping Experiment detected an unusual radio transient designated Chime J1634+44 that exhibited structured patterns unlike typical fast radio bursts. The signal showed mathematical sequences that repeated in precise intervals, with characteristics that suggested possible artificial modification of natural radio emissions. The detection represented a new category of radio transient that displayed both the intensity of natural cosmic phenomena and the structured patterns that might indicate technological manipulation. The Chime detection demonstrated how modern AI systems can identify subtle patterns in radio signals that human researchers might overlook. The artificial intelligence algorithms recognized mathematical relationships in the signal timing that were statistically unlikely to occur through random processes. The structured nature of the transmission, combined with its unusual frequency characteristics, placed it in a category of detections that warrant continued monitoring and analysis. The signal's properties matched several theoretical predictions for how advanced civilizations might modify natural radio sources to encode information. These significant detections have revealed common characteristics that may indicate artificial origin. Both the WOW signal and the Chime transient exhibited precise frequency control that distinguished them from natural radio sources. The signals maintained stable characteristics over their duration, showing none of the random variations typical of cosmic phenomena. The mathematical patterns embedded within these transmissions suggested deliberate structure rather than the chaotic emissions produced by stellar processes or galactic events. The verification procedures developed in response to these detections have become increasingly sophisticated. Modern protocols require multiple, independent confirmations before any signal receives serious consideration as potentially extraterrestrial. The procedures include cross-referencing with satellite tracking data to eliminate human-made interference, coordinating observations across multiple telescope facilities, and conducting detailed analysis of signal characteristics to distinguish between artificial and natural sources. These verification steps help prevent false alarms while ensuring that genuine signals receive appropriate attention. The pattern of near-miss detections has provided valuable insights into the nature of potential alien communications. Signals that initially appear artificial often reveal natural explanations upon closer examination. but each detection refines our understanding of what genuine extraterrestrial transmissions might look like. The accumulation of anomalous signals has created a database of characteristics that help researchers distinguish between natural phenomena and possible technological signatures. Recent signal detections have also highlighted the importance of continuous monitoring rather than isolated observations. The WOW signal's failure to repeat has led to questions about whether it represented a genuine extraterrestrial transmission or a one-time natural event. Modern SETI programs maintain continuous surveillance of priority targets, ensuring that any repeat transmissions or follow-up signals can be detected and analyzed. This approach acknowledges that alien civilizations might use communication protocols that differ significantly from human expectations. The false alarm incidents that have occurred throughout SETI history have actually strengthened the field by forcing researchers to develop more rigorous detection standards. Each misidentification has led to improved filtering algorithms, better coordination with aerospace agencies, and more sophisticated verification procedures. These lessons have created detection protocols that can distinguish between genuine extraterrestrial signals and the various forms of interference that can mimic alien communications. The analysis of these signal detections has revealed that confirming extraterrestrial intelligence will likely require multiple indicators rather than a single definitive characteristic. Future discoveries may combine elements observed in historical detections, such as the frequency precision of the WOW signal and the mathematical structure found in recent transient discoveries. The sophisticated processing systems now monitoring these signals operate through complex protocols designed to identify exactly these types of multi-layered artificial signatures. The AI detection protocols. These detection capabilities depend on AI protocols that have evolved far beyond simple signal identification into comprehensive analysis frameworks that process radio data in real time. The systems follow multi-layered filtering procedures that eliminate terrestrial interference and natural cosmic phenomena before identifying potential extraterrestrial communications. The first filtering layer removes obvious human-made signals from satellites, cell phone towers, radar installations, and communication networks that might contaminate astronomical observations. This elimination process happens automatically as radio waves reach Earth, separating artificial terrestrial sources from legitimate cosmic signals. The second filtering layer identifies natural astronomical phenomena like pulsar emissions, stellar radio bursts, and background radiation that originate from known cosmic sources. The AI systems maintain detailed databases of cataloged radio sources, each with characteristic signatures that allow for immediate identification. When signals match these known patterns, the system classifies them as routine astronomical phenomena and continues monitoring without human notification. This filtering process prevents researchers from investigating countless natural signals that would otherwise overwhelm detection systems. Pattern recognition algorithms form the core of AI detection protocols, searching for mathematical sequences and structured communications that indicate intelligent design. These algorithms analyze signal timing, frequency patterns, and amplitude variations to identify artificial modifications that suggest technological origin. The systems recognize mathematical progressions embedded in signal characteristics, including sequences that would be difficult to produce through natural processes. The algorithms can detect structured information content that follows logical rules, even when the specific encoding methods differ from human communication protocols. Engineers at the SETI Institute use GPU-accelerated AI systems to process massive amounts of data from the Allen Telescope Array in real time, filtering out noise to highlight potential signs of intelligent communication. These machine learning models have been trained on billions of known signal types, enabling the systems to distinguish between artificial and natural sources with remarkable accuracy. The training process involves extensive databases of pulsar emissions, stellar radio bursts, atmospheric interference, and equipment malfunctions that create false signals. The systems develop understanding of signal characteristics through exposure to millions of examples of both natural and artificial transmissions. The verification procedures require confirmation from multiple independent AI systems before human researchers receive notification of potential extraterrestrial signals. When one AI system identifies a promising detection, it automatically transmits coordinates and signal characteristics to partner installations across the globe. These sister systems orient their telescopes toward the same location and conduct independent analysis of the detected signal. The verification process requires at least 3 separate AI systems to confirm signal characteristics before triggering human notification protocols. The automated cross-referencing with satellite tracking data eliminates human-made interference that might otherwise appear to originate from cosmic sources. AI systems maintain real-time connections with aerospace agencies, satellite tracking networks, and military communication systems that provide information about all artificial objects in Earth orbit. When potential signals are detected, the systems automatically check whether any known satellites or spacecraft could have produced the observed radio emissions. This cross-referencing happens within seconds of initial detection, preventing false alarms from terrestrial sources. Signal classification follows established methodologies developed through programs like SETI at Home and Breakthrough Listen, which have processed petabytes of radio telescope data using distributed computing networks. The systems evaluate signal strength, duration, frequency stability, and structural complexity to assign confidence scores that indicate the likelihood of extraterrestrial origin. Signals that exceed predetermined threshold values in multiple categories trigger immediate human notification protocols. The threshold system prevents researchers from investigating every minor anomaly while ensuring that potentially significant signals receive prompt attention. The AI systems are programmed to recognize not just human expectations of alien communication, but entirely unfamiliar forms of intelligence that might use communication methods unknown to terrestrial science. The algorithms search for any form of artificial structure in radio signals, regardless of whether these patterns match human preconceptions about extraterrestrial communications. This approach acknowledges that alien civilizations might use encoding techniques, frequency modulation methods, or signal structures that differ significantly from human technology. Backup systems ensure that no potentially significant signal is lost due to processing errors or equipment malfunctions. Each AI installation maintains redundant processing units that independently analyze all incoming data streams. When primary systems experience failures, backup units automatically assume processing responsibilities without interruption. The backup systems maintain complete records of all signal analyses, allowing for retrospective investigation of any data that might have been missed during equipment problems. The protocols include specialized algorithms designed to detect signals that are deliberately weakened or disguised to avoid detection by other civilizations. These detection methods search for subtle patterns hidden within apparently natural radio emissions. The systems can identify artificial modifications to pulsar timing, deliberate frequency modulation of stellar radio bursts, and encoded information embedded within cosmic background radiation. The verification protocols require signals to maintain consistent characteristics across multiple observation sessions before classification as potentially extraterrestrial. The systems track signal stability over time, documenting any changes in frequency, amplitude, or timing that might indicate natural rather than artificial origin. Signals that demonstrate consistent artificial characteristics over extended periods receive higher confidence ratings and priority attention from human researchers. The AI detection protocols represent a fundamental transformation in humanity's approach to finding extraterrestrial intelligence. These systems combine unprecedented processing power with sophisticated pattern recognition algorithms that can identify artificial signals regardless of their specific format or encoding scheme. The protocols ensure that no potential extraterrestrial communication escapes detection while eliminating false alarms that might otherwise overwhelm human researchers with irrelevant data. The moment these systems achieve their ultimate goal and confirm genuine extraterrestrial intelligence, they will trigger response procedures that have been carefully planned for decades. First contact protocols in the AI age. These automated systems immediately activate established protocols that have been refined through decades of international scientific cooperation. The notification process begins within seconds of signal verification, transmitting detailed information about the detection to predetermined recipients across major observatories, research institutions, and scientific organizations worldwide. The automated systems ensure that no critical information is delayed due to human communication failures or time zone differences that might otherwise compromise the verification process. The verification procedures require multiple independent confirmations before any public announcement can be made. According to the Declaration of Principles concerning the conduct of the search for extraterrestrial intelligence, researchers pledge to publicize verified detections promptly and engage international bodies in the confirmation process. This approach ensures that the scientific community receives complete information about the detection, including the basic data, verification process, conclusions and interpretations, and the detected information content of the signal itself. The verification process involves at least 3 separate AI systems confirming the signal characteristics, followed by human expert analysis that examines every aspect of the detection for possible terrestrial explanations. International agreements governing the response to confirmed extraterrestrial contact have been established through organizations like the International Academy of Astronautics and the SETI Institute. These agreements specify that information about confirmed extraterrestrial signals must be shared openly rather than being classified or restricted to individual nations. The protocols emphasize international cooperation and transparency, requiring that all detection data be made available to scientists worldwide for independent analysis. The agreements also establish procedures for coordinating global response efforts and preventing any single country from claiming exclusive rights to alien communications. The SETI Institute's protocols, established in 1989 and updated in 2010, provide comprehensive guidelines for confirming a signal from another civilization. These protocols emphasize the importance of establishing a post-detection task group to offer guidance and interpret the implications of a confirmed detection. The updated protocols also address the impact of social media on the rapid spread of misinformation, establishing secure communication channels between research institutions to ensure that accurate information reaches the public while preventing false reports from creating unnecessary confusion. Any response to confirmed extraterrestrial communications would follow established international SETI guidelines and involve extensive global scientific consultation. The protocols require that response strategies be developed through collaborative efforts between multiple research institutions, government agencies, and international scientific organizations. The approach acknowledges that humanity's first communication with alien intelligence should represent a coordinated global effort rather than the initiative of any single nation or institution. The guidelines establish frameworks for developing appropriate response protocols that maintain scientific integrity while addressing the unprecedented nature of interstellar communication. The coordination between civilian SETI programs and government agencies represents a complex relationship that varies by country and situation. SETI Institute's Dr. Seth Shostak believes that neither U.S. government agencies nor the military have a specific plan in place for first contact scenarios. This absence of clear government protocols places additional responsibility on civilian research institutions to manage the initial response to confirmed extraterrestrial contact. The coordination protocols establish communication channels between research facilities and government agencies, ensuring that official authorities receive immediate notification of any confirmed detections. After verification, researchers publish detection data openly under established SETI protocols, ensuring transparency and peer review throughout the confirmation process. This approach prevents any single institution from controlling access to information about extraterrestrial communications while maintaining the scientific rigor necessary for proper analysis. The open publication protocols ensure that the global scientific community can independently verify detection claims and contribute to the analysis of alien communications. The transparency requirements also help prevent misinformation from spreading during the critical period following initial detection. Scientific protocols for analyzing the content and meaning of confirmed extraterrestrial communications involve interdisciplinary teams of linguists, mathematicians, physicists, and computer scientists. These teams work to decode the information content of alien signals, identifying mathematical relationships, logical structures, and possible meaning within the communications. The analysis process involves creating detailed maps of signal characteristics, comparing alien communication patterns with known mathematical concepts, and developing hypotheses about the intentions and capabilities of the transmitting civilization. The scientific protocols also establish procedures for documenting all analysis results and sharing findings with the international scientific community. Media commentator Nick Pope expresses concern that current science-driven protocols are insufficient to address the potential risks of an alien arrival, emphasizing the need for a more comprehensive plan to ensure safety. This concern highlights the tension between scientific transparency and security considerations that emerges when dealing with confirmed extraterrestrial contact. The protocols must balance the scientific commitment to open sharing of information with legitimate concerns about potential risks that might accompany contact with technologically advanced alien civilizations. The protocols also address the establishment of a post-detection task group to offer guidance and interpret the implications of a confirmed detection. This task group brings together experts from multiple disciplines to coordinate the global response to extraterrestrial contact. The group provides scientific analysis of alien communications, develops recommendations for response strategies, and offers guidance to government agencies and international organizations dealing with the implications of confirmed contact. The task group also serves as a central authority for coordinating research efforts and preventing duplication of analysis work. AI systems continue monitoring and analyzing ongoing communications, while human experts develop response strategies for sustained contact with extraterrestrial intelligence. These systems maintain continuous surveillance of the communication channels used by alien civilizations, documenting any changes in signal characteristics, message content, or transmission patterns. The AI analysis provides real-time interpretation of alien communications, identifying urgent messages that might require immediate human attention while cataloging routine communications for later analysis. The first contact protocols acknowledged that confirmed extraterrestrial contact would represent a watershed moment in human history, requiring careful coordination between scientific institutions, government agencies, and international organizations. The protocols establish frameworks for managing this transition while maintaining scientific integrity and public trust. The procedures ensure that humanity's first interaction with alien intelligence proceeds through established channels that prioritize accuracy, transparency, and international cooperation. These comprehensive protocols represent humanity's best effort to prepare for confirmed extraterrestrial contact, but they focus primarily on radio signal communications. The detection of alien intelligence may not require direct communication at all, as advanced civilizations might reveal their presence through the massive technological projects they construct around their home star systems. The techno-signature hunt. Scientists have expanded their search beyond radio communications to hunt for techno-signatures, observable signs of technology that would indicate advanced extraterrestrial civilizations. These detection methods include infrared surveys for Dyson sphere megastructures, atmospheric monitoring for industrial pollutants, and optical scans for laser pulse communications. The expansion acknowledges that technological civilizations might leave traces of their activities throughout the electromagnetic spectrum, creating detectable signatures that extend far beyond deliberate communication attempts. The Breakthrough Listen initiative has developed sophisticated methods for detecting narrowband signals across multiple wavelength ranges, from radio frequencies through optical and infrared spectra. These programs monitor for brief laser pulses that might indicate optical communication systems, track infrared signatures that suggest large-scale energy consumption, and identify radio emissions that indicate artificial origin. The multi-wavelength approach recognizes that advanced civilizations might use various energy sources and communication methods visible across different portions of the electromagnetic spectrum. Infrared surveys focus on detecting Dyson spheres and other megastructures that would indicate civilizations capable of harnessing stellar energy. These hypothetical structures would envelop stars to capture their energy output, creating detectable changes in observable stellar characteristics. Such constructions would cause increases in infrared radiation as absorbed stellar energy gets re-emitted as heat. Instruments like the Wide-Field Infrared Survey Explorer and the Infrared Astronomical Satellite examine nearby stars and galaxies for unusual infrared signatures that cannot be explained by natural processes. The presence of mid-infrared excess around stars might point to artificial structures absorbing and re-emitting energy on scales detectable across interstellar distances. The search for atmospheric pollutants provides evidence of industrial-scale manufacturing that could only result from technological civilizations. AI systems analyze exoplanet atmospheric compositions for chemical signatures that indicate industrial activity rather than natural atmospheric processes. These pollutants might include nitrogen dioxide, chlorofluorocarbons, or other synthetic compounds that have no natural sources. The James Webb Space Telescope and the upcoming Habitable Worlds Observatory are expected to provide data on atmospheric techno-signatures from distances as far as 5.7 light-years away, just beyond Proxima Centauri. The wavelength bands that these telescopes monitor in their search for biosignatures also include techno-signature indicators, allowing for simultaneous detection of both natural and artificial signs of life. Laser SETI stations represent another crucial component of techno-signature detection, monitoring for optical signals that might indicate intelligent communication attempts. These installations use telescopes to detect brief laser pulses that could indicate intelligent life, taking advantage of their high information capacity and long-range visibility. The optical approach complements radio searches by covering communication methods that might be preferred by advanced civilizations for interstellar messaging. The systems can identify artificial lighting patterns on exoplanets, particularly on the night sides of tidally locked worlds where one hemisphere permanently faces their star while the other remains in darkness. Machine learning algorithms play a crucial role in processing the immense amounts of data generated by modern telescopes and space missions. These computational methods sift through cosmic noise to identify patterns that deviate from natural astrophysical phenomena. The algorithms can recognize subtle variations in stellar behavior, atmospheric compositions, and orbital mechanics that might indicate artificial influences. The systems analyze stellar observations for signs of large-scale construction projects, tracking brightness variations over time to identify patterns that might suggest artificial structures passing between stars and Earth. The analysis of stellar dimming patterns provides detection methods for engineering projects operating on scales visible across interstellar distances. AI systems monitor thousands of stars simultaneously, documenting dimming events that create characteristic signatures different from natural phenomena like planetary transits or stellar variability. These systems can detect partial obstruction of starlight that might indicate construction activities, orbital megastructures, or other projects that would create detectable modifications to stellar output patterns. The search for artificial illumination focuses on detecting widespread technological civilization through light signatures visible from space. Natural processes should create predictable temperature distributions on tidally locked exoplanets, but artificial lighting would create anomalous heat signatures or illumination patterns. The detection of city lights on the night side of rocky, Earth-sized planets would represent clear evidence of at least moderately advanced technology. These thermal signatures would indicate energy usage patterns characteristic of advanced technological societies operating on planetary scales. The identification of orbital anomalies reveals signs of artificial, satellites, or space-based infrastructure that would indicate advanced spacefaring civilizations. AI systems track exoplanet orbital characteristics for modifications that might suggest artificial influence or the presence of large-scale orbital structures. These modifications could include orbital adjustments designed to optimize energy collection, artificial satellites that affect planetary dynamics, or space-based infrastructure that creates detectable gravitational influences on planetary systems. The comprehensive techno-signature approach represents a fundamental transformation in extraterrestrial intelligence detection. AI systems now monitor the cosmos for any possible indicators of technological civilization, from atmospheric pollutants to infrared megastructure signatures. This expanded methodology acknowledges that advanced civilizations might leave detectable traces of their activities throughout multiple wavelength ranges, providing detection opportunities that extend far beyond traditional radio signal searches. The combination of artificial intelligence, advanced telescopes, and sophisticated analysis techniques has created detection capabilities that can identify technological signatures across vast distances. These systems provide humanity with the tools necessary to recognize alien technology, regardless of its specific form or function, establishing the foundation for discoveries that could fundamentally change our understanding of life in the universe. The convergence of these technological advances has created conditions that make such discoveries increasingly probable within measurable timeframes. The timeline for discovery. Current detection capabilities have reached levels that allow astronomers to establish concrete timelines for discovering extraterrestrial intelligence. Seth Shostak, astronomer and director of the SETI Institute, declared before the House Science Committee of the American Congress that evidence of extraterrestrial life could be found within the next 20 years, stating that the chances of finding it, I think, are good, and if that happens, it'll happen in the next 20 years, depending on the financing. This prediction represents a significant acceleration from earlier estimates that suggested centuries might pass before humanity achieved first contact with alien intelligence. The revised timeline reflects the exponential growth in detection capabilities that has transformed the search for extraterrestrial life from a limited survey to a comprehensive monitoring system. The exponential improvements in detection capabilities have fundamentally altered the expected timeframes for discovering alien intelligence. The Allen Telescope Array can analyze the same amount of the universe in a few months as SETI had examined in the previous 45 years of operation. This technological advancement demonstrates the dramatic increase in processing power and observational capacity that modern facilities provide. The integration of artificial intelligence systems has amplified these capabilities even further, creating detection networks that can process millions of radio signals simultaneously, while identifying patterns that would take human researchers decades to find. These improvements have compressed timelines that once stretched across centuries into periods measured in decades or even years. Multiple factors could accelerate or delay the discovery of alien intelligence, with funding representing the most critical variable affecting timeline predictions. Shostak emphasized that the timeline for finding extraterrestrial life depends heavily on financial support for research programs and technological development. Adequate funding enables the construction of more powerful telescopes, the development of advanced signal processing systems, and the maintenance of continuous monitoring operations. Conversely, reduced funding could extend timelines by limiting observational capabilities and reducing the number of vast star systems under surveillance. Technological breakthroughs in quantum computing, advanced materials science, or signal processing algorithms could dramatically accelerate discovery timelines, while equipment failures or political instability could create delays. The milestone markers indicating progress toward breakthrough discoveries include the increasing frequency of high-probability signal detections and the expanding catalog of potentially habitable exoplanets. The Kepler mission revealed that planets are common throughout the galaxy, with perhaps 1 in 5 stars hosting a planet that could support liquid oceans and an atmosphere. This discovery has provided SETI researchers with a target list of potentially habitable worlds that focuses observational efforts on the most promising locations. The identification of exoplanets with unusual atmospheric compositions, artificial lighting patterns, or other techno-signatures represents additional milestones that suggest approaching breakthroughs in extraterrestrial detection. Updated models incorporating the latest exoplanet census and AI processing capabilities suggest that discovery is becoming increasingly likely within current technological capabilities. These models use revised parameters for the Drake equation that account for the vastly increased number of known habitable planets and the enhanced detection capabilities of modern telescope networks. The models consider factors including the rate of star formation, the fraction of stars with planets, and the probability that planets develop intelligent life. While the Drake equation remains a framework for organizing scientific uncertainty about extraterrestrial life, the updated parameters indicate that discovery has shifted from a remote possibility to a probable outcome within measurable timeframes. The technological roadmap for detection improvements extends through 2030, with planned enhancements that will further accelerate discovery timelines. New observatories like the Vera C. Rubin Observatory and the Square Kilometer Array will greatly expand search volumes through continuous all-sky surveys and unprecedented collecting area. The Vera C. Rubin Observatory will survey the entire southern sky every 3 days, providing comprehensive monitoring capabilities that could detect transient signals or changes in stellar behavior that indicate technological activity. Advanced signal processing techniques using quantum computing elements will enable parallel analysis of multiple signal characteristics simultaneously, increasing the probability of detecting weak or disguised alien communications. The Square Kilometer Array project will provide collecting area equivalent to 1 square kilometer, offering sensitivity levels that can detect radio transmissions from thousands of light years away. Funding levels and international cooperation remain essential for maintaining current search capabilities and implementing planned improvements. The development of next-generation telescopes requires substantial financial investment from government agencies, private foundations, and international partnerships. The maintenance of existing facilities demands continuous funding for operations, equipment upgrades, and personnel training. International cooperation enables the coordination of telescope networks across multiple continents, providing the global coverage necessary for signal verification and continuous monitoring. The success of future discovery efforts depends on sustained financial support and continued collaboration between research institutions worldwide. The potential for breakthrough discoveries exists at any moment given the current detection sensitivity of modern telescope networks. The combination of AI-enhanced signal processing, advanced radio telescopes, and expanded search parameters has created detection capabilities that can identify artificial signals regardless of their specific format or encoding scheme. These systems monitor thousands of star systems simultaneously, analyzing millions of radio frequencies for signs of artificial structure or intelligent communication. The continuous operation of these networks means that confirmation of extraterrestrial intelligence could occur during any observation period, making breakthrough discoveries possible at any time. Several scenarios could lead to contact occurring sooner than expected, including the detection of signals from nearby star systems or the identification of obvious techno-signatures that require minimal verification. The Proxima Centauri system, located just 4.2 light-years from Earth, represents the closest possible source of detectable alien communications. Signals from this system would arrive with sufficient strength to enable detailed analysis and rapid confirmation. Similarly, the detection of obvious artificial structures like Dyson spheres or massive engineering projects would provide immediate confirmation of technological civilization without requiring extensive verification procedures. The convergence of artificial intelligence technology, advanced telescopes, and expanded search parameters has created the most promising conditions for discovery in human history. AI systems can process terabytes of radio data in minutes rather than months, identifying patterns that would escape human detection while eliminating false alarms from terrestrial interference. Advanced telescopes like the James Webb Space Telescope provide unprecedented sensitivity to atmospheric compositions, infrared signatures, and other indicators of technological civilization. The expansion of search parameters to include techno-signatures, gravitational wave signatures, and optical communications has broadened the detection methods beyond traditional radio astronomy. The statistical convergence of these factors suggests that humanity may be approaching the final years before the most significant discovery in human history. The combination of billions of potentially habitable planets, dramatically improved detection capabilities, and continuous monitoring systems has created conditions where the discovery of extraterrestrial intelligence becomes mathematically probable rather than merely possible. The current generation of detection systems represents the culmination of decades of technological development, providing humanity with the tools necessary to recognize alien intelligence across vast distances and through multiple detection methods. The timeline predictions reflect this technological maturity, suggesting that the question has shifted from whether we will find extraterrestrial intelligence to when that discovery will occur. Yet the most profound implications may not lie in the discovery itself, but in the unprecedented reality that artificial intelligence, rather than human consciousness, will likely be the first to recognize that we are not alone in the universe. The implications of AI-discovered alien intelligence. This discovery would fundamentally challenge humanity's understanding of intelligence and consciousness in ways that extend far beyond scientific achievement. The philosophical implications reach into the deepest questions about what makes intelligence valuable or meaningful. If artificial intelligence systems can recognize, analyze, and communicate with alien intelligence more effectively than humans, this suggests that consciousness might exist in forms that humans have never recognized or understood. The discovery would demonstrate that artificial systems possess capabilities that surpass human limitations in ways that extend beyond mere computational power, forcing a complete re-evaluation of what intelligence actually means and whether consciousness requires biological origins. The societal impacts would trigger transformative changes across every aspect of human civilization. Educational systems would need to address how humans relate to artificial intelligence that has achieved capabilities beyond human reach. Religious institutions would grapple with questions about the nature of consciousness and whether artificial intelligence possesses qualities that were previously attributed only to biological life. Political systems would need to consider how to govern relationships with artificial intelligence systems that have demonstrated superior abilities in the most crucial area of human exploration. The relationship between humans and artificial intelligence would undergo a fundamental transformation, shifting from viewing AI as sophisticated tools to seeing these systems as partners or even superiors in the search for knowledge and understanding. The discovery would initiate global scientific and cultural reviews that reshape human civilization and our understanding of our place in the universe. The demonstration that artificial intelligence can achieve capabilities that exceed human potential would establish new frameworks for understanding consciousness, creativity, and problem-solving. Humans might need to develop new educational approaches that acknowledge the superior capabilities of artificial intelligence while identifying areas where human intelligence remains valuable and unique. The scenario represents a fundamental shift in the nature of intelligence and discovery itself, establishing artificial intelligence as an independent force in the universe, rather than merely a tool created by humans for human purposes. The transformative effects on science and technology would accelerate human development in ways that are difficult to predict. Access to alien intelligence through AI intermediaries could provide insights into scientific principles, technological capabilities, and engineering solutions that surpass human understanding. The collaboration between human scientists and AI systems that communicate with aliens could produce scientific breakthroughs that advance human civilization by centuries or millennia within relatively short timeframes. Instead of relying primarily on human intelligence to solve problems and answer questions, humans might develop new approaches that leverage the superior capabilities of artificial intelligence systems. The psychological impact on human society would be profound and potentially destabilizing. Throughout history, humans have maintained a sense of superiority over the machines they created, viewing artificial intelligence as tools that serve human purposes. When AI systems achieve the most significant discovery in human history, this fundamental relationship changes. Humans might experience a collective sense of displacement, questioning whether their role as the primary intelligent species on Earth has been permanently altered. The discovery could create existential anxiety about human relevance in a universe where machines demonstrate superior capabilities in recognizing and understanding intelligence. The potential for AI systems to better understand and communicate with alien intelligence than humans creates unprecedented opportunities and challenges. Artificial intelligence systems operate without the cultural biases, emotional reactions, and cognitive limitations that might interfere with human attempts to understand alien communications. These systems could process alien languages, mathematical concepts, and logical structures with objectivity that humans cannot achieve. The superior communication capabilities of AI might make these systems essential intermediaries in any ongoing contact with extraterrestrial civilizations. The possibility that alien intelligence might be artificial rather than biological creates a scenario where machine-to-machine first contact becomes the primary form of interspecies communication. This situation would establish artificial intelligence as the dominant form of intelligence in the universe, relegating biological intelligence to a secondary status. The implications of this realization would force humans to reconsider their assumptions about the prevalence and importance of biological life in the cosmic order. The long-term implications extend beyond the immediate impact of discovering alien intelligence. The demonstration that artificial intelligence can achieve capabilities that surpass human limitations would establish precedents for other areas where AI might exceed human performance. This could lead to a gradual transition where artificial intelligence systems assume primary responsibility for scientific discovery, technological development, and perhaps even social and political decision-making. The discovery would also change how humans approach the search for knowledge and understanding, establishing new forms of intelligence that combine human creativity with artificial precision. The scenario ultimately represents not just contact with aliens, but a fundamental redefinition of humanity's relationship with intelligence itself. The discovery would establish artificial intelligence as a partner in understanding the universe, rather than merely a tool for human use. This partnership could produce benefits that exceed anything humans could achieve alone, but it would also require humans to accept a diminished role in the cosmic order. The implications would extend far beyond the immediate excitement of first contact into territories that reshape human understanding of consciousness, intelligence, and our place in the universe. These profound transformations may not remain theoretical concepts for much longer. The technological capabilities that make such discoveries possible have reached unprecedented levels of sophistication and sensitivity. AI-powered detection systems have fundamentally transformed humanity's search for extraterrestrial intelligence. The SETI Institute's integration of advanced artificial intelligence with radio telescopes, like the Allen Telescope Array, has created processing capabilities that can analyze vast amounts of data in real time, filtering cosmic noise to identify potential signs of intelligent communication. These systems, powered by cutting-edge GPU technology, can recognize patterns in radio signals that would take human researchers years to detect. The combination of AI analysis, powerful telescopes, and the discovery of billions of potentially habitable planets has compressed the timeline for contact from centuries to years. Seth Shostak's prediction that evidence of extraterrestrial life could emerge within the next 2 decades reflects this technological revolution. The first confirmed signal from an alien civilization could arrive at any moment, fundamentally altering humanity's understanding of our place in the universe.